Well, yeah, probably we can start. Good afternoon, everybody. Welcome to this session of the seminar series. Today we have with us Niccolò Tonicello from the International School for Advanced Studies, SISSA, in Trieste, Italy. And well, I will just mention very shortly that I had the pleasure to meet Niccolò when I was in SISSA for my research day in 2021 before he went for his postdoc in Stanford. And as in representation of the Kratos research group here in SIMNE, we appreciate that he accepted the invitation to deliver this seminar. Hopefully we will be able to continue cooperating with SISSA's MATLAB and in the future. So I will not mention too much about our speaker's background because he has some slides about that. I will just mention that he has a bachelor and a master's from the University of Padua. He then did his PhD in France in Université de Normandie. And then he did, as we said, his postdoc in Stanford University, and where he will mention a little bit about that. Today's talk is about high-order methods for CFD, and he will also mention later on something on PINs, physics and foam neural networks. So without, before giving the word to Niccolò, I would just like to recall everybody that this session is recorded, and usually in the seminars, we let the speaker conclude, and then we will have some minutes at the end for questions. So thank you. And
well, thank you, Raul, for your nice presentation. Well, I'm very happy to be here, of course, and have the chance to present some of my recent research on generally, let's say, two-phase flows. As Raul mentioned before, I will just go very briefly into my curriculum, essentially to just ease the path into what I will talk in terms of science. I say I did my Bachelor and Master Degree in Mathematical Engineering at the University of Padua, where I started to, let's say, get interested in numerical methods for fluid dynamics. After that, I moved in France to do a PhD more focused on high-order methods for compressible turbulence. So still, let's say, something related to, well, CFD, of course, but more into the compressibility part and turbulence. After that, I moved to the US at Stanford University, where I did a postdoc on phase field methods for multiphase flows. And finally, I moved back to Italy, well, pretty much 1 year ago now, where I'm working on disorder models and deep learning for turbulent compressible flows and as well multiphase. So today's talk will be essentially on the part related to multiphase, both in terms of high-fidelity, so essentially like high-order methods for compressible two-phase flows, and a small part on physics-informed neural networks, so essentially, yes, surrogate modeling for the same type of applications. One little introduction as well on my current group of research. As Raul mentioned, you already know Professor Gianluigi Rozza, who's the PI in my group in Trieste, where the main, let's say, business is on reduced order models for CFD. There's a long history on application of reduced order modeling for incompressible laminar flows, restructuring interaction, and of course as well in hemodynamics. And only recently we are moving into this the part related to turbulence, compressible flows, two-phase flows, which are my let's say field of expertise. A little overview of the presentation. In the first part, I will essentially present two different schemes, high-order schemes for compressible two-phase flows, based on the conservative Alenkane equations, coupled with the five-equation model to resolve the velocity field needed to adapt the interface. In the first part, we'll be focused on a quasi-conservative discontinuous Galerkin framework, and secondly, we will essentially move into a spectral difference methodology in order to, let's say, ease a little bit the constraints that we found into the discontinuous Galerkin approach. Finally, last few slides will be focused on physics-informed neural networks for Alenkane equations and for two-phase flows. So, as I mentioned, I will start from this five-equation model within a discontinuous Galerkin framework. The most, let's say, it's very well known in the community. The most popular, let's say, numerical schemes for CFD are finite differences and finite volumes. Whereas finite differences, it's pretty easy to increase the order of accuracy. Sometimes can be a little bit complicated to deal with unstructured meshes. Whereas for finite volume, it's complicated to increase the order of accuracy, but they are very flexible from a geometrical point of view, and that's why they are very popular and can deal with very, very complex unstructured meshes. The discontinuous finite element, which is, let's say, a larger group of numerical schemes, which including the discontinuous Galerkin and spectral difference that I will introduce later on, are some kind of combination of the two, because within the element, you still use high-order polynomial, similar to what is, let's say, under the hood in finite differences, and then the information is transmitted across the different elements using numerical fluxes, which are very similar to what is commonly used within the finite volume community. These type of methods can allow very fast convergence due to the high-order approximation. For similar reasons, they are characterized by low numerical dissipation, which is very important when you deal with turbulent flows or in general with under-resolved solutions. And finally, they are also very interesting from from the geometrical point of view due to their intrinsically high-order framework that can be used to deal with complex geometries as well. In terms of physics, what I will essentially discuss today, it's mostly based on the phase field concept and on the Ahlenkhan equations. The idea is very simple. Essentially, you define an indicator function that varies between 0 and 1 to distinguish the two different phases. And let's say differently from respect to the volume of fluid, where you have a sharp interface, this indicator function will be characterized by a smooth transition between the two different phases. This indicator function is affected by the velocity field that is resolved using a larger set of equations. And the additional terms that I'm showing here are the ones connected to the conservative Ahlenkhans, whose role is to keep this interface of the fixed thickness while it's affected. In fact, the two main ingredients is essentially just a diffusion term that will allow the interface to spread if due to the velocity field itself gets too over thin, and a term of sharpening, which depends on the normal vectors with respect to the interface, will define later on and are particularly challenging terms to be evaluated, which instead are responsible to sharp the interface if it's over diffused, once again due to the velocity field or due to numerical dissipation. Of course, it's very important to have a good equilibrium between these two different mechanisms, and the main parameters associated to these are essentially gamma, which you can let's say imagine is quantifies the ratio between this whole sharpening diffusion mechanism and advection. So essentially, it needs to be fast enough so that it can counterbalance the distortion due to the velocity field, and that's why it's usually taken to be proportional to the maximum velocity or the maximum value of the velocity field in your domain, and epsilon, which is related to the interface thickness, and that's why it's usually taken to be proportional to the grid size, so that under mesh refinement you will converge towards an exact discontinuity. This is also important. We'll come back later on in terms of that it's showing the way essentially to the numerical scheme, to the physics informational network, to whatever method you're using to solve the equations, to gently converge towards something that is ideally discontinuous. This is just one equation, of course. The Ahlenkhan part is just responsible for the dynamics of the interface, but of course the interface gives you information on the different phases in terms of different densities, different transport coefficients, and of course it's affected via a certain velocity field that needs to be resolved using other balances. Here I'm considering the 5-equation model, where you consider a balance for, of course, for the people online it's going to be difficult, but I'm just going in order from on the left side from top to bottom, the conservation of mass of the first phase, conservation of mass of the second one, and a conservation of momentum and total energy, which are considered to be the same for both phases. This is a reduced model with respect to the general Bernoulli setup, where you have different velocities, different densities, different energies between the different phases. And of course, you have to, similar to what happens for compressible flows, you have to close this system with an equation of state relating, let's say, temperature to density and pressure. One additional information is that I mentioned before that the sharpening term will depend on the normal vectors, and these normal vectors are particularly challenging to be evaluated. Usually they are defined as the gradient of phi divided this magnitude, so they define the direction of the phase field. But of course, you can understand that here I'm showing an example of phi. They are kind of ill conditioned because they are either like the profile is flat, so the gradient will tend to 0 and you will have a 0 at the denominator, or they will have very strong gradients that close to the interface. So there are a lot of different tricks in order to evaluate these normal vectors in an accurate way. An approach that I'm following here is essentially the one to advect another function I'm calling psi, which is only used to compute the normals. And this function psi, as you can see here, it's some kind of relaxed version of the phase field phi. So just looking at the essentially the interface capturing technique. So you suppose you have your velocity field is known, then you have only to solve these two equations, like you have the advection of the phase field with the Alencamp terms, and this additional function psi. But it's kind of intuitive to see that if you just evolve the system, at some point, these the isolines defining the interface of these two functions, at some point they will start to decouple because, well, let's see if I can do it once again. Yes, because you will have psi information coming back to the phase field equation. You're using psi to compute the normals, but there's no information flowing back from the phase field to the this additional function psi. And that's why we need to take, let's say, some inspiration from the level set community, and you have to reinitialize. Essentially, you stop your simulation, you take your phi at some fixed time, and you integrate in pseudo time this reinitialization equation, so that you will reconstruct psi based on your value of phi. And long story short, essentially solving this equation will essentially gives you convergence towards a level set type of function. So it's a sign distance function where it's, of course, as you can tell, much easier to compute derivatives on, like perfectly smooth at the interface at least, without moving the interface itself. So the isoline psi equal to 0 corresponds exactly to the isoline phi equal to 0.5. So you're not moving the interface, you're just regularizing psi. And once you do that, you can continue with your time integration. Just one detail, we don't need, with respect to the previous figure I showed about psi, we don't really need a fully converged solution. At the end of the day, you just need psi to be smooth enough close to the interface so that you can compute the normals accurately and then use these normals inside of the phase field equation. So this video is just to tell you how normally this type of equation behaves and what's the purpose in general of reinitialization. Once you do that, now the coupling is both ways. So you need psi to compute the normals, but at some point you reinitialize psi using information of phi and continue this loop. So moving into this part, in terms of, let's say, numerical tests, it's always interesting to consider first just the interface capturing technique. So there are a few cases which are particularly of interest where you just prescribe velocity field and you just see how the integration of these two equations will behave. So it's interesting in terms of, for example, of mass conservation errors, so that you want that if the velocity field U is divergence free, you want the mass of your fluid is always conserved. And of course, we will also look into the effect of the order of accuracy in terms of the discretization. A classical test case for this kind of problems is the Rayleigh-Cotta vortex, which essentially, like as you can see, the velocity field is imposed, and is essentially consists in this droplet, which is stretched into a thin ligament, and then is stretched back into the initial condition. This is, of course, very interesting for the fact that you have a very challenging region close to the tail, and of course you come back to the initial condition, so it's a suitable test case to evaluate convergence and in general like how the whole integration will affect the general shape of the droplet. In terms of mass conservation errors, we evaluated essentially just the integral of this phase field at a given time minus the initial time in normalized. And here I'm essentially comparing two different evaluations of this mass conservation error for different orders of approximation. Of course, once again, the errors are not identically equal to zero, because the previous equations are written in a non-conservative form, because I will go into the compressible part. I mean, because this is a compressible formulation, so it's not necessarily, I cannot write it in a conservative form because the divergence is not equal to zero. And I'm considering different orders of approximation within a discontinuous Galerkin framework. And we can observe that, well, first of all, for different grid sizes, like I'm showing different refinements, this error goes to zero, and it's equal to 10 to the minus 8/9 for the second order approximation on the coarsest grid. But if we increase the order, keeping the same number of degrees of freedom with respect to the second order, we can actually decrease this error in a very, very significant way, so that the coarsest mesh will give you already 10 to the minus 11 or 12 in terms of mass conservation errors, showing this is actually been observed for different type of high order methods, that you can reduce in a significant way the mass conservation errors, increasing the order of accuracy of your numerical scheme. As I mentioned before, essentially we want to, well, first of all, like observe the behavior in general, like the influence of the order of accuracy in terms of the goodness of the solution. And we can observe that, for example, in the second order of approximation, and I will show similar things also for other test cases, you have this tendency of alignment of the interface with respect to the grid. You will have this spurious behavior, deformation essentially of the interface whenever, in particular, you are under-resolved, whereas where everything is well resolved, the approaches are pretty similar. And you will also notice that at some point this will be reflected also in the final form of the droplet after the full integration. Whereas, yeah, I mean, and again, all these the second order approximations are worse than the fourth order, also in terms of the final shape of the bubble. Just to give, let's say, a few details on the numerics, I don't want to get too technical because there's a lot of demonstrations and proofs in terms of how we can obtain this kind of results. Essentially, the whole system, in terms of 5-equation model, as I mentioned before, is written essentially in a quasi-conservative form, so that, I mean, the phase field is including a non-conservative term in terms of the transport term, and all the other balances instead, of course, they have a conservative terms in terms of advection. And it can be proved that the quasi-conservative form, coupled with a Lax-Friedrich Riemann solver within the DG framework, and an ad hoc discretization of the phase field equation, which consists in applying twice the integration by parts and the specific numerical flux that I want to avoid to write. gives you also the interface equilibrium condition. Essentially, when you are in a compressible flow and you have constant pressure, constant velocity, and just a material interface, so a discontinuity only in the density, you want your numerical scheme to preserve this exactly. I mean, you don't want to pollute the pressure or velocity with oscillations, and you want to preserve exactly this kind of scenario. And this kind of ingredients can be proved that if the pressure is perfectly flat and velocity is perfectly flat at some time step, at the next time step, this is exactly the same. And I will also show that this applies for a different scheme with a different type of trick, let's say. Also, all these different terms that I didn't mention before, essentially the first term, the versions of A1 are the Allen-K terms, but since you are modifying essentially some kind of mass conservation equation, you have to apply consistent modification to all the balances for more physical reasoning. So in order to have, for example, that for constant density rho 1, you have to get exactly the same equation 1 multiplied by rho 1, and also you have to essentially like reobtain the divergence-free condition if all densities are constant. All these kind of constraints will lead to additional terms in the different equations. And once again, if you, for example, modify the mass conservation, like the total mass conservation, so the sum of the two partial masses, this will affect momentum, and it's pretty well known that if you modify momentum, of course, this influences kinetic energy and so on. So you have to all keep this in mind in terms of correction to the other balances. So in terms of now, we can move to essentially the two-phase test. So where the velocity field is actually resolved through the whole 5-equation model full system. And the test case that I will consider essentially, well, first objective is just to test from a numerical point of view that interface equilibrium condition is indeed fulfilled also from a numerical point of view. And once again, I'm interested in seeing how the interface deformations can happen for high density ratios for different type of for different orders and different resolutions. So a classical test, which seems pretty simple but can be kind of challenging, is a simple bubble advection to test that you're able to preserve the interface equilibrium condition. As I was mentioning before, essentially the velocity field, the initial velocity field is perfectly constant, pressure is perfectly flat, and you have instead a high density ratio between the two different phases. Of course, the resolution of the whole system should give you just an advection of the phase field, and all the other quantities should be constant, like velocity and pressure. So you should get something similar, just an advection of the bubble. Here, I'm showing on the left the initial pressure and the pressure after 5 periods. And you can, of course, notice that the deviations from the unitary value of the pressure are order of 10 to the minus 11 and doesn't change over time integration, showing that we are indeed able to preserve the interface equilibrium condition. This same kind of test will come back later on with a different scheme, with a different approach, but this is still an important, let's say, sanity check in terms of your numerical scheme to preserve this kind of scenario. Secondly, once again, in terms of like influence of the order of accuracy, it's quite well known that this test case is interesting also for long time integration because everything is periodic, so you can integrate as long as you want, and of course you want your numerical method to preserve the right behavior for as long as possible. And it has been observed with different numerical schemes for high order and low order that usually after some time, for low order approximation, you start to have some deformation of the bubble, which are essentially related to the way you evaluate the normals and the accumulation of numerical errors in this evaluation. Whereas for the fourth order approximation, after 5 periods, the shape of the bubble is essentially the same with respect to the prescribed initial shape. Secondly, we started to essentially, you will see in following the presentation, we are continuing to increase essentially a little bit the complexity in terms of the physics, and here we consider as well, like for the radiator instability, the additional viscosity and gravity, which leads to primary breakup. Essentially, you have a heavy fluid on top of a light fluid, and this will start to merge in the mix and the heavy fluid going into the light fluid downwards. And for our numerical meter, we get essentially like very close results with respect to the literature. Once again, we are interested in seeing what happens for the discretization, how the discretization will influence the goodness of the result. And here we are comparing a second order approximation with a fifth order approximation at different times. And we can observe essentially, I don't remember if, no, okay, sorry about that. Okay, so we can observe, first of all, that even at kind of early times, you already see some differences between the two different simulations. And in particular, where you have like high curvature of the interface. In fact, the whole concept of the Allen-Kahn equation is try to keep the thickness constant across the normal direction of the interface. And of course, the resolution along the normal direction cannot really improve varying the order, because it's you are trying to fix the thickness. But the evaluation along the tangential direction instead can have some benefits in using the higher order approximation. So it's going to be a better approximation in dealing with these particular regions. Of course, this will deviation will start like this, and then they will continue to evolve and continue to accumulate for the low order cases, leading, for example, here to even a loss of the symmetry of the problem due to this accumulation of numerical errors. Also, yeah, I mean, and again, this is also again due to the fact that you will see here you have some type of deformation that tend to align with respect to the grid size, to the grid directions, and lead to this type of asymmetric solutions. Finally, this is just a very brief comment in terms of, let's say, computational flexibility. Here, with respect to volume of fluid or this kind of methodologies where you have to reconstruct the solution, and it depends a lot on the geometrical properties of your mesh and how to deal with that. The fact that we are basing everything on essentially just additional terms in the equations is a very natural generalization to different type of grids. Here, so we consider also the same framework for triangles, and without doing any particular modification to the, say, to the interface capturing part. Everything has all the fluxes, of course, are different depending on the mesh type, but the part related to multiphase is essentially the same. You get very, very similar results. Of course, you get practically same type of behavior whenever everything is well resolved. When you have breakup, of course, the influence of the different type of elements might influence the general behavior of the numerical scheme, and you get some differences. But the general behavior is very, very similar also on triangular meshes. Finally, we also consider the addition of surface tension for this setup, and it's important to highlight the fact that in surface tension you need the normal vectors. Those are fundamental in order to have a good modeling of surface tension, and this comes back to the fact that I'm considering a specific, let's say, approach to evaluate these terms, and this will reflect also on the goodness of the results where you consider as well surface tension. So this is a classical rising bubble test case where you essentially have this light fluid moving upwards, and this is a very classical problem for validation. And in fact, we get pretty good agreement with respect, for example, to this work by Manzanero from the Ferrer group in Madrid, where essentially they did the similar things within a discontinuous Galerkin approximation, but with Canadian. So the numerical framework is pretty similar, and you're getting essentially very, very similar results in terms of location of the bubble, final shape, and essentially the velocity of the bubble moving upwards. So, as a general, just a brief summary of this part. Within this discontinuous Galerkin framework for the fabrication model, we are able, using the high-order properties of the numerical scheme, to keep low the mass conservation errors. All the different, let's say, ingredients in the numerical scheme, such as Lax-Friedrich, and the form of the equation allows for the interface equilibrium condition. You have these benefits in the high order in terms of the deformations of the interface, which are significantly reduced using the high order approximation. A relatively simple way to generalize to unstructured meshes, whereas there are a few, let's say, there are not problems, but limitations of this approach. They use the fact that we have to use the Lax-Friedrich flux in order to preserve the interface equilibrium condition. I didn't mention, but we need like also over integration to evaluate the flux terms in the discontinuous Galerkin in order to avoid aliasing issues. And also, well, this is not a limitation, but the fact that we didn't consider properly high compressible cases with shock capturing. That's what led us to consider a more flexible framework, which is the spectral difference scheme, which is still a spectral element type of approach, but it's collocated, and there are many different, let's say, ingredients and components that we can move a little bit easier with respect to the TG framework. So just as a introduction of the spectral element, the spectral difference method, it's still a spectral element type of scheme, which is based on two different set of points within the element. Solution points, which are inside the element, and flux points, including also the extrema of the element. The idea is to use just standard Lagrange interpolation, known the solution at the values at the solution points. Doing so, it's possible to evaluate this variable at the flux points, including the extrema. Similar to what is done in, let's say, in the finite volume kind of approaches. Once you know the values at the interfaces, you can define numerical fluxes at the interfaces and correct the value of the fluxes at this location. Now that you have flux on all the flux points within the element, you can define a different type of interpolation on this set of points, so on the flux points. This is very important because essentially you will have a high order interpolation on the fluxes with respect to the variables due to the relationship, let's say that the divergence of the fluxes gives you the variables, and this is key in keeping the high order approximation of the scheme. And finally, once you have all this interpolation is fully analytical, you have these known Lagrangian polynomials, and you can just interpolate back to the solution points and apply the divergence, and then you will have essentially the whole divergence term, and you can advance your solution with your favorite time integration scheme. The idea within the multiphase part, essentially here, it's very, very simple. It's taken from this work on spectral difference method for combustion, but the concepts are very similar, is that we can just simply make a change of variables and using, instead of the conservative variables, the primitive variables for the interpolation purposes, because I was saying that, for example, for the interface equilibrium condition, pressure is perfectly flat, velocity is perfectly flat. You want to use these type of functions in the interpolation step instead of using steep profiles like momentum or energy. So you just pass from conservative to primitive. You consider the Lagrangian interpolation based on these variables, so that you can evaluate this quantity at the flux points, and then you can move back to the conservative variables and continue the same type of reasoning of the spectral difference approach. This should help in avoiding oscillations due to interpolating something that is very steep. So I'm coming back to the same type of method that we considered before, the same type of test case that we considered before, just the advection of a bubble. Once again, you want pressure to be perfectly constant. And if we consider the conservative variables approach, what usually happens, and that happens as well, for example, in combustion, is that close to the interface between different materials, if you don't do things right, you will start to have like these pressure oscillations that will essentially continue to grow and lead to the simulated instability of the simulation. In fact, this happens even for relatively low order approximation, so even like numerical dissipation is not gonna help you in this case. Whereas if you consider this change of variables and interpolate the primitive variables, this behavior is it completely disappears because you're interpolating something which is perfectly constant, so you don't have any issues in doing so. Now that we are in this framework, essentially we can consider something a little bit more, let's say, the way that we fulfill the interface equilibrium condition is very straightforward, it's very localized, it's just change of variables, so that we have all the flexibility and all the other, let's say, components of the numerical scheme. So we essentially, I didn't want to show you all the other cases. We reconsider all the Rayleigh-Taylor and rising bubbles, etc. But we wanted to like push a little bit more in terms of compressibility. So we consider this classical problem of the shock bubble interaction. This interaction of a helium bubble in air at Mach number equal to 1.22. And here you have all the type of behaviors. You have the shock interacting with different mediums, so propagating differently inside of the bubble and outside. You have breakup, different reflections. There are plenty of physics going on in this case. We use this problem once again to compare this conservative versus primitive approach. And even if for this case, actually, weirdly, the conservative approach is still stable, which tells a lot of the previous test case that seems very simple, but is usually very challenging. But however, okay, this is not with this screen is not great. Sorry about that. But essentially, you will have some oscillations. You will still have some oscillating behavior close to the interface of the pressure with respect in the conservative form, rather than using this change of variables in terms of primitive variables. Also, another sanity check to see that we are not polluting the solution with any pressure oscillation at the interface. Here, once again, we are within a high order method with shocks, so we need to somehow deal with it. And we consider an artificial viscosity, let's say a Laplacian artificial viscosity for this problem with an indicator that should be active only in presence of the shock. So we consider the pressure as a good indicator. And as you can see, it's always active exactly where the shock is and never at the interface, showing that it's able to actually track only the shock, and there's no oscillation close to the interface that causes the sensor to be active where it shouldn't be. So this is another way of seeing that everything is correct in this sense, that it's the right, essentially the right variable to sense, to use to detect the shock, and there's no activation close to the interface. So in terms of the spectral difference framework, essentially we were able to preserve interface equilibrium condition with a different type of flavor. Consider also the artificial viscosity as shock capturing, and also we have more flexibility in terms of Riemann solver, so we don't need anymore the use of the Lux-Friedrich solver, and you can use different type of Riemann solvers as well, which is more important when you consider under-resolved cases, but that I'm not showing here, but can be a powerful, let's say, addition to the numerical scheme. Finally, the last part of the presentation. How am I doing with time? Like 10 minutes, 5, whatever. It's not long. It should be.
You see, officially 17. So.
Okay. That's fine.
For questions, 10.
Okay. So essentially, we wanted to see a completely different framework. I mean, we just talked about high order methods, classical solvers, essentially for this kind of applications. But yeah, I think you know pretty well that fixed info neural networks are becoming very, very, very popular in many different applications. And we developed in the last few months, started to do some research on applying these kind of techniques to the same kind of framework. So the idea of physics in neural networks is pretty straightforward. The idea is that you want to essentially describe your solution itself as a neural network of the input of the spatial coordinates, and through automatic differentiation, there's a way to essentially obtain the gradient of the output with respect to the inputs. And since the output is the solution and inputs are spatial locations, essentially there's a way to evaluate gradients of the solution itself, so that the general loss of the neural network, you can actually use PDEs. So you can prescribe that certain functions of the solution itself and its gradient to be close to zero. So there's a component which is the operator loss, which is going to be the residual of your PDE that you want to solve. In addition, you have also, as in classical, let's say, solvers, you want to fulfill boundary conditions, initial conditions, and sometimes also data loss if you have your solution at some prescribed locations. In our case, we will not consider the case of data loss, so it's going to be a completely unsupervised framework where you just have there's no data involved, essentially. Just want to interpolate your solution as a neural network and make it to solve a PDE. So everything is done within this PINA package that has been developed at SISSA MATLAB in the last few years. It's a physics info neural network for advanced modeling Python softwares to solve PDEs. You have plenty of, like, it's highly sectorized, customizable, multi-device. It's based on PyTorch Lightning, and you have plenty of easy tutorials to start if you want to take a look at GitHub. We have plenty of examples on how to use it with different methodologies and different frameworks. So in terms of using PINs for this kind of problems, it's quite well known that the solution to implicit conservation laws, in general, like things with discontinuities, are quite challenging within a physics info neural network framework. Well, this is the case as well for classical numerical methods. First of all, there are some issues in terms of the expressivity of the network. Like similar to numerical scheme, you have to solve the interfaces. So you have to describe many different scales. You have to be able to solve the thickness of the interface and all the other smooth regions of the flow field. There are some theoretical results on the bounds between residual and solution. So in some cases, even if you reduce your residual, it doesn't mean that your solution is actually close to the right solution that you're expecting. And as well, you have some issues in terms of training, so that, of course, you are trying to get something discontinuous. Evaluating the gradients is always complex, and it's complicated to get to the right solution. So that's why finding these kind of things to choose-phase problems can be quite challenging for these methodologies. So we cannot really advect discontinuous function, at least, like, it's very complicated because exactly discontinuous, evaluating the gradients is very complex. So what we thought is to reframe everything in terms of diffuse interfaces. So similar to standard numerical schemes, we want to consider something a little bit more relaxed. But of course, like what I presented today, essentially, if you try to advect a diffuse interface, at some point, some parts of the interface will be deformed by the velocity field. So sometimes it's going to be too diffuse, sometimes too thin, and you will have some issues when you actually start to couple these with a full solver to prescribe the right transition between different phases. That's why we consider essentially the same with using the Alencamp terms as a way to avoid this kind of behavior. So again, as a type of correction with respect to standard transport of a diffuse interface. In doing so, you can get exactly the right thickness everywhere, and the right behavior of the bubble dynamics. So it's easier to train with respect to discontinuous function because it's diffused, but at the same time you can keep the thickness constant, so you can actually preserve the right type of physics that you want to have, so not having over thinning or over diffusion of the interface. An interesting part that we are investigating right now is essentially the fact that when for full order solvers, like high fidelity solvers, you have all these framework to preserve certain properties, like as I was saying before, the interface equilibrium condition, mass conservation, whatever. Here, it means you have no guarantee of all of these things. So we wanted to essentially quantify at least the errors in mass conservation or in the dynamics of the problem. On the left, I'm showing the mass conservation errors using the pins based on the Allen-Kahn equation and without Allen-Kahn, and these are pretty similar. It's a little bit larger, the one without the one with Allen-Kahn, because essentially you are evaluating more terms on which you are making more numerical errors, so you lose a little in terms of mass conservation, but in terms of this total surface of the bubble, we can observe, I'm here comparing the two different pins without and with Allen-Kahn, and comparing with the high fidelity solver. And due to the fact that the interface is over diffused, so that you're not doing anything about the interface, you will get a profile of the total surface of the bubble, which is completely different from what you expect in this kind of problem. Instead, with Allen-Kahn, we are actually able to preserve the right thickness and consequently the right dynamics of the bubble, which is pretty, and that's why the physics informal network based on Allen-Kahn is very close to the high fidelity solver. Another detail in terms of like the improvements that we can get using this kind of surrogate modeling is that here we're using actually epsilon, which is equal to 5 times 10 to the minus 3, and just a 30 times 30 grid to evaluate the residual. And in the high fidelity solver, to get the same accuracy, you actually need 200 times 200 as a grid, and many more time steps. And of course, this high fidelity solver has been run on a cluster, whereas the pin, even if the training can take some time, is still way less expensive than the high fidelity solver for these problems. Secondly, okay, oops, sorry, here you should have epsilon. Secondly, we want to see what happens if we continue to decrease epsilon, essentially. You have a certain type of convergence study. We want to decrease epsilon and see how the different physics informal neural network will behave, because you might expect that the errors in transporting something that is diffused, the errors will decrease as you make this function sharper and sharper. I mean, all of them, both pins based on per transport and Allen-Kahn, they should get the same exact results when the function is exactly discontinuous. But from a practical point of view, this doesn't happen. I mean, even if, like, consider the Allen-Kahn and decreasing the value of epsilon, so moving more and more towards something which is exactly discontinuous, you get the right behavior of something which is essentially periodic, that you get at the half of the period, you get the maximum stretching, and then you get back exactly to the right, to the initial state. Whereas using pure transport, actually you get something which is converging, I guess, at some point, but to a totally different type of dynamics, so that you will always pollute the surface, total surface of your bubble, and after a full period, you will get something which is larger. The surface will be larger than you would expect. Now it's appearing, sorry, the epsilon. So this last part instead was essentially focused on the use of physics informal neural networks for two-phase flows. In particular, let's say it's more about just kinetic tests I've been showing and the whole relationship with these additional Alencon terms, which can be seen as some kind of regularization of sharp transporters. So you are helping the physics for neural network to converge to the right solution prescribing these additional terms, which is still pretty similar to what you actually do also in the standard solvers. You have this kind of transfer learning using simple transport, meaning that you are also to train the Alencon pin. We essentially use a simple transport and again use the Alencon terms as some kind of correction, some kind of helping the standard pin based on just transport to get the right solution. In terms of, let's say, limitations, and we are working on this right now, the fact that here we're using a relatively vanilla type of pin within a space-time formulation, so you're not doing anything different in space and time. You are just locating residual points in space and time and try to reduce the residual as much as you can without any concept of causality or in general like of autoregression. So maybe these are options that we can explore in order to get better results for this framework. And finally, as I mentioned, we are considering only kinematic tests here. We are currently working on the coupling everything with Navier-Stokes in incompressible formulation or not. In general, like not prescribing the velocity field itself to the Alencon equation. As a general summary of today's talk, I presented two different type of high-order methods for compressible five-equation model with this additional methodology to evaluate accurately the normal vectors. Both approaches are able to preserve the interface equilibrium condition in different ways with different techniques, and showing the advocating the benefits in using high-order discretization for this kind of application. Finally, I spent some time in presenting these physics for neural networks for Alencon, where we use Alencon as a type of regularization for the advection of discontinuous functions. Currently, I'm working on increasing the complexity of the physics. So in dealing with turbulent flows, I'm adding, well, I already showed some results actually with surface tension and phase change in terms of, let's say, transfers at the interface. And we are currently working on a fully coupled two-phase formulation for the physics-informed neural networks. If that's not enough, of course, like this is my website, my email, all the details also of MATLAB, and over there the QR code for PINA and all the to see all the different developments in terms of methodology of this package. So thank you for your attention, and yeah. Yeah, we have time for a couple of questions. Okay.
Can you go back to the second part of your presentation when you talk about the spectral difference and the flux forms?
Sure.
So
I
anticipate my question so you can know. First of all, thanks for your talk. It was very interesting. My question was is about this approximation of the fluxes that you use. Are you introducing an extra variable like in a mixed formulation to approximate the fluxes? Are you doing some reconstruction?
No, I mean, yeah, everything is essentially like in reconstruction. Like the variables are always like the unknowns are always just the conservative variables.
Okay.
It's just a matter of like, yeah, interpolating these values, change the type of interpolation when you consider the fluxes,
yes,
and then applying the divergence to this new type of interpolation. So, I mean, in a way, you could say that I could access to those fluxes as a different variable defined on a different set of points.
Yes.
But at the end of the day,
it's not
just,
what you're doing.
no, it's not. I mean, the resolution at the, let's say, when you get here, and you have the divergence of the fluxes evaluated at solution points, then you have time derivative of the solution evaluated at those points plus the divergence equal to 0. So you just evolve the conservative variables over time. So the only variables that I'm actually solving, that I'm considering, are the conservative variables.
Okay. So follow-up question, if I may. Did you experience any sensitivity to the mesh construction because of this reconstruction of the fluxes?
I mean, for the case that I consider here, like for the spectral difference, actually here everything is Cartesian, and there are no issues for this formulation in terms of the multiphase part. Of course, there are other people, and my former advisor and friends have been using this for the single-phase compressible part, and there are plenty of studies with pretty deformed type of meshes where we didn't experience any type of no major issues in doing this. Even the other way around, like they've been using this type of willingly badly looking meshes just to evaluate the robustness of the scheme, the behavior of numerical dissipation, dispersion for the four meshes without major issues.
Okay.
Well, not even minor. I don't want to say minor issues, without any problem.
No problem. Some background, and just out of curiosity, you said at the first part of the discontinuous galerkin, you were not doing anything. It's not that you cannot cope with shock factoring, but you were not doing anything special, at least.
Yeah.
And then with the spectral difference, you are able to. But despite this, what do you think are the main challenges or limitations that you have towards a real world application of this? Is it ready? Is it a little bit far, or how do you see this?
Well, I mean, in this, to be honest, for all, let's say, discontinuous Galerkin and spectral difference, once again, they can deal with complex geometries and so on. But also for the unstructured mesh, it's relatively simple type of mesh. I never had any experience in dealing with really complex type of geometry. So for sure, the geometrical part is still a challenge. And maybe it's one of the main, let's say, issues in IO emitters, that there are still some work to be done in terms of stability, essentially. Okay. So, for example, here I'm not using any dealizing type of techniques. So when you will have to deal with under-resolved, I mean, for example, in turbulence. For turbulence, there are still some work to be done, so that the models need to be tailored for this type of schemes, because any type of, let's say, general model or right off the shelf type of models might fail. You might still have some oscillations due to the higher order approximation that you need to deal with in a specific way. But I hope that I will soon show you some real case scenarios.
I missed one part at the beginning, for the fee and so for the level set you were saying, and how does it work? So
okay, 1 second. Let's say the interface capturing something like, okay, wait a second. I mean, these are the two slides essentially. This one and the one afterwards. So
each side should be positive, and it's the zero level set who is giving you the two phases, or
no, I mean, yeah, the phase field is used to distinguish the phases. It's this indicator function varying between 0 and 1 that used to distinguish the phases. Psi, which is kind of a level set, is just used to computing the normals. And this, essentially, I mean, of course, you have some computational cost in addition, because you are considering both, but at the same time, you are avoiding, for example, one drawback of using level set is that you reinitialize the function that uses to distinguish the phases, and the reinitialization is not mass conservative. So here I'm using level set only to compute the normals, and the actual work of distinguish the phase and so on, it's all on the phase field.
you have
So
all the cutting of the elements and everything to know exactly where the elements are cut. You have to do all these numerics to understand where you cut the element, and then to
no, I mean, everything here is, let's say, in a Euclidean framework. I mean, the mesh is never like deformed, changed identify the isosurface be equal to 0.5 or level set equal to 0 is just for visual purposes. At the end of the day, what I'm doing here, I'm literally just taking phi, translated like by 0.5 to have a level set type of function, so that the interface is at equal to 0, evolving 0 times this function, and then the final value of this whole system will give me the new side that I'm testing. So there's nowhere something which is specific to the in-element reconstructions or where the actual interface is. I would say, I don't know if I've been clear.
You need to use this function to really test the elements and have like a sharp interface.
No. I mean, again, the idea is similar to, I always like to say that this is kind of a shock capturing kind of thing. Like you would like to have something which is discontinuous, but of course the numerical scheme cannot handle something. In this Fourier order, you have Gibbs phenomenon, you have oscillation, you cannot have something discontinuous, you have to have diffuse it a little. In shock capturing, you have additional viscous terms. In multiphase, you have to have both. You have to have something which is diffusing interface and sharpening at the same time. So you have adding terms in order for your scheme to deal with as a normal function, as a smooth profile that you can interpolate.
Can you do it explicitly?
Yeah, everything is explicit in time. As you, I think here you have more experience in incompressible. For compressible flows, usually, it can be pretty painful to do implicit time integration. Can be done, of course, but here I'm doing everything explicitly.
Well, if there are no more questions, we just thank Niccolò again. And